Did you know that cassava or tapioca, a root which is consumed by millions in Asia and parts of Africa, if eaten unprocessed, can kill you? Yes, cassava aka tapioca contains enough compounds which, when consumed, can be broken down into hydrogen cyanide, the same lethal poison which was used in chemical warfare. And 50 milligrams of hydrogen cyanide, if absorbed into your blood, can kill you. Let's look into the chemistry behind this. Cassava contains a class of compounds called cyanogenic glucosides, which can produce hydrogen cyanide via a series of reactions which take place in our human body. And it is astounding to know that 100 grams of unprocessed or raw cassava contains enough cyanogenic glucosides to produce 50 milligrams of hydrogen cyanide. And 50 milligrams of hydrogen cyanide is about the permissible limit in human blood. Consumption of cassava, which can produce more than 50 milligrams of hydrogen cyanide, can turn out to be lethal. So, unprocessed cassava is actually like a locked box. It is safe as long as it is not crushed or chewed. But once you crush or chew the box, the contents are opened and the lethal poison comes out. Now let us dive deeper into the chemistry behind how cyanogenic glucosides are broken down into hydrogen cyanide. Let us start with a simple chemical reaction, the cyanohydrin synthesis. Okay, now let's look at the cyanohydrin synthesis. Let me bring up my screen here. Right, cyanohydrin synthesis. Right. We'll be talking about the reaction where we prepare cyanohydrins from aldehydes or ketones. Both aldehydes and ketones are carbonyl compounds, which means carbon is doubly bonded with oxygen. So a sigma bond and a pi bond to oxygen. So let me draw the structure here. C double bond O. Right. It has sp2 hybridization and trigonal planar geometry, which means it's like a flat plane, and C, that is carbon, double bonded with oxygen, one group here, another group here. So if some attack happens at the carbonyl center, it can happen from both directions, and steric hindrance is not part of the picture because it's planar. Right. Or steric hindrance can become a part of the picture but not a major part. Right. Now, looking at electron densities, we need to understand how electrons are distributed at the carbonyl center. So, carbon is comparatively electropositive with oxygen, and oxygen being the second most electronegative element, it sucks up the entire electron cloud towards itself, leaving carbon relatively electron deficient, and thus the carbonyl center, especially in the case of aldehydes, is an extremely good electrophile. So by aldehydes, I'll put a hydrogen here. So this is an electrophile, right? So what happens is oxygen ends up with a partial negative charge because of its high electron density, and carbon ends up with a partial positive charge due to its relatively low electron density. So carbon is electron deficient, right? Now for the synthesis reaction, we'll be adding an ionic cyanide such as NaCN or KCN. So cyanide is C triple bond N, and carbon has a negative charge because of its lone pair. Or not because of its lone pair, it contains 5 electrons in total if you look at this. So 1 electron is excess from its usual state, so 1 negative charge. It has a negative charge, and the highest occupied molecular orbital, HOMO, highest occupied molecular orbital, as the name suggests, when you draw the molecular orbital picture of cyanide, you find that the orbital with the maximum energy is the sp orbital. Right. Sorry. Yeah. So when you look at cyanide, it contains a negative charge. Carbon is looking for an electrophile to give off its negative charge and form a bond. So Cn minus is the nucleophile here. Nu- uh, just a minute. Nucleophile. Right. So Cn minus is the nucleophile and aldehyde or ketone is the electrophile. Now let's look at the reaction and the mechanism of the reaction of cyanohydrin synthesis. So moving to the mechanism part, so I'll draw the structure once again here, plus Cn minus. I'll ignore the three bonds between carbon and nitrogen from now on, but just know that they are there. So you have a electron deficient carbonyl center here and a highly electron rich cyanide here. So it's natural to expect that the cyanide will attack the carbonyl center, and that's exactly what happens. So cyanide adds to the carbonyl center. This is an addition reaction, and what forms as an intermediate is the tetrahedral intermediate CO minus. What happens is, in terms of molecular orbital theory, cyanide, as I mentioned earlier, has the highest occupied molecular orbital as the sp orbital of carbon, and the lowest unoccupied molecular orbital of the aldehyde is the pi star orbital. So electrons from the sp orbital of cyanide, the nucleophile, is transferred into the pi star orbital of aldehyde, and when the pi star orbital is filled, the pi bond is broken. Right. See, the beauty behind molecular orbital theory is any complex reaction can be explained in terms of molecular orbital theory, and it can be a powerful tool to predict the mechanism of the reaction. So the pi bond is broken and oxygen takes up the electrons, leading to O minus right here, and you have the hydrogen right here, and cyanide adds to the structure here. Carbon of the cyanide loses its negative charge as it forms a bond with the carbonyl carbon. Right. A couple of things to notice here is the tetrahedral intermediate formed here is relatively unstable, because when you consider cyanide, it's an extremely good leaving group, which means it is capable enough to retake its negative charge and move out of the tetrahedral intermediate. To go into details of leaving groups, I suggest you go through Claydon, Warren and Greaves textbook, and the section on leaving group ability and pKa values. I'm not going into details as it is not relevant for our discussion here, but those who are interested can go in. Right. So the tetrahedral intermediate formed here is relatively unstable, and thus this step is in fact reversible. So I need to change the arrow mark here and make it a reversible reaction. Right. So once the tetrahedral intermediate is formed, in the cyanohydrin synthesis what happens is you have some group which can donate a H plus to oxygen and thus form C, Cn, H and OH. This compound formed here is called cyanohydrin. Right. Now let's discuss about the reversibility part here. So when cyanide adds on to the carbonyl center, sp2 hybridized carbon is converted into the sp3 hybridized tetrahedral intermediate. So from a planar structure, it is moving into a tetrahedral three-dimensional structure. So the problem is the three-dimensional structure is crowded. Steric hindrance comes into picture, and also cyanide, as I mentioned, is an extremely good leaving group. So Cn minus can actually just leave from the tetrahedral intermediate from here, and the reverse reaction can happen. And this does happen if it is present in, say, H2O. water, and the reverse reaction actually dominates over here. Now we need to understand this because what actually happens in the case of cassava is the reverse reaction. Now let's dive deep into what happens in the case of cassava. So let me change the color over here. Right. So let's move on. I hope you understood the mechanism well. You can always refer back because the mechanism is quite important in the case of cassava. Right. Cassava contains, as I mentioned earlier, a cyanogenic glucoside. The most prominent one being linamarin. Right. Now let's look at the structure of cyanogenic glucoside linamarin in this case. So as the name suggests, glucoside, it has to do something with glucose. Explains why tapioca is an extremely good source of carbohydrates. So let's look at the structure of linamarin. It has a structure extremely similar to glucose, except there is an extra additional group attached here, which is the cyanohydrin path. Right. You have an OH here, an OH here, an OH here in the axial position. Then you have a CH2OH here. Right. This is linamarin. If you noticed the mechanism earlier, you already know how a cyanohydrin looks like. And if you carefully look here, you can already find the backbone of cyanohydrin right here. This is the trouble creating part, the lethal part. So what happens is, we'll move to the reaction, just a second. Right. Inside our body, when cassava is crushed by our teeth and churned in our stomach, what happens is there are certain enzymes in our body itself, such as beta glucosidase and hydroxynitrile lyase, which can break down linamarin to produce hydrogen cyanide. And this is exactly the reverse reaction which happens in the case of cyanohydrin synthesis. So that was the need to understand the mechanism of cyanohydrin synthesis. Now, looking at this OH, OCN, right? OH, OH in the axial position, and OH, right? This compound first reacts with our enzyme beta glucosidase, and this produces acetone cyanohydrin, which is OH, CN. This is a byproduct which is formed, and glucose is released as another product. So it produces energy, but the byproduct formed is lethal because, as we discussed, it can undergo the reverse reaction, which actually happens here in the presence of another enzyme called hydroxynitrile. So I don't have space here, I'll write it here, nitrile lyase. So what this does is it breaks down, or it helps cyanide to leave as a leaving group, producing acetone and HCN. So how HCN? CN minus leaves. So I will draw the mechanism over here. So CN minus leaves here. The bond between oxygen and hydrogen is broken, and this forms the pi bond. In detail, if you want, you can just sketch up the mechanism, and you can find that Cn minus abstracts a proton and forms HCN, and the remaining structure forms acetone. So hence the name acetone cyanohydrin. Anyway, HCN is produced. Now this is the HCN which is problematic. Let me reiterate here, and I want this to be remembered. Yeah. 100 grams of cassava can produce 50 milligrams of HCN, or I should say unprocessed cassava, can produce 50 milligrams of hydrogen cyanide, and consumption of merely 50 milligrams of hydrogen cyanide, if absorbed into blood, is fatal. So this is the chemistry behind the cyanohydrin synthesis, and behind how cassava can turn out to be a deadly killer. Now let us understand how processing cassava actually helps. So when you process cassava, what you do is you break it up, you either ferment it or boil it and remove the water. So what happens is when you break it up, the same process which should have happened if you had not processed it, which should have happened inside our body, happens outside our body in the container, and the enzymes in cassava itself plays a similar role and releases hydrogen cyanide from cassava and leaving behind the starchy part. So when you drain off the water, hydrogen cyanide can dissolve in water, and when you drain off water, it is removed via the water and you get the safe consumable part of cassava. So this is why processing it and then only eating it is essential. So now that you understand chemistry of cassava, you find that chemistry is not just confined to labs, but you understand its beauty in real life cooking, food, and how traditions guarded this chemistry and how traditions helped in protecting us from lethal effects of such compounds. Just a side note, there are a class of other seeds which contain such compounds which can produce hydrogen cyanide. For example, apricots or apple seeds contain similar compounds which can produce HCN. So be wary of eating, say, apricots to on large amounts. If eaten in small amounts, it's safe, but large amounts can be problematic. So stay safe and keep wondering. Thank you.